So today we are going to learn about calculating a way to quantify how much solute is dissolved in a solution. You can kind of think about if you are making Gatorade and you put just like 1 scoop of mix in versus like 8 scoops of mix in, that the one with 8 scoops would be more concentrated and the one with 1 would be more dilute. But now we actually have language for how we can discuss that. And the wording is molarity. So that's how we would describe a solution. This is a solution with a molarity of 8.5, or we would say a 3.8 molar solution. And what that would mean would be how many moles of solute, so moles of the thing that we are dissolving, per liter of solution. So not liter of water that we're adding it to, but after the solution is mixed, how much the mixture, the solution is. And we can abbreviate molarity with a capital M. That's also the unit at the end. So when we say like 3.8 molar, it's 3.8 capital M, or we could say 3.8 moles per liter, just like that. Either one of those is perfectly acceptable. So we're going to start thinking about molarity and especially thinking about how we actually make a solution. We need to use a very specific piece of glassware. This glassware is called a volumetric flask. It is used for making solutions exclusively, and it only has one marking on it, like one volume reading, but that one volume reading is very specific, very accurate. So the first question says, how do we make 250 milliliters of a 1.34 or 1.43 molar NH42Cr2O7, that's ammonium dichromate. That's the name of that ionic compound that is dissolved in that solution. So the first thing we need to do is we need to calculate the mass of the ammonium dichromate that we need. And I didn't leave myself room enough to do these calculations, but I know on your piece of paper you do. So the formula is molarity equals moles per liter. If I want to calculate the mass, the first thing I'm going to do is I'm going to calculate the moles, and then I'm going to convert from moles to grams. So I know that the molarity is 1.43 capital M. I don't know the number of moles that will be dissolved, but I know that my total volume will be 250 milliliters. But notice that the unit for the bottom is not volume, it's liters. So this has to be converted from 250 milliliters to liters, right? There's 1,000 milliliters in 1 liter. So I divide this number by 1,000. So I'm going to get 0.250 liters as my total volume. And then when I multiply those two numbers together, my number of moles is equal to 0.3575 moles. And I am not going to round that, because now what I'm going to do is I'm going to convert that to grams. I know that 1 mole of that substance equals, and now I have to find the molar mass of this. The molar mass of this whole thing right here. So I have to look and see how many nitrogen, right? So this is a multiplier. So there's going to be 2 times 14.01. That's the mass of nitrogen. There's going to be 8 times 1.008. 2 times chromium is 52.00, and 7 times 16.00. When I multiply and add those all together, it's a big number, 252.084 grams. And then when I multiply that by 0.3575, I get 90.12 grams, and to 3 significant figures, that's 90.1 grams of ammonium dichromate. So down here, you can see step number 2, mass out the amount, so that 90.1 grams, and add it to a 250 milliliter volumetric flask with a small amount of water in it to begin to dissolve the solid. So on a piece of whey paper here or in a whey boat, I mass out 90 grams. The image from the textbook only uses, rounds it to 90.0. I add that and with a little bit of water in it, mix to dissolve, and then I fill the volumetric flask up to the mark. Notice that I actually didn't wind up adding all 250 milliliters of solution. I wound up adding less than that because those ions of ammonium and dichromate, those take up volume. So that's why it's so important that we say that its molarity is moles per liters of solution. So I didn't add 250 milliliters, but my final solution had a volume of 250 milliliters. And so all these problems that we're going to do for the rest of the notes today are going to be using these formulas. Molarity equals moles per liter, and just reading the question, substituting what we know, and solving for what we don't. So calculate the molarity of a solution made by adding 15.5 grams of NaCl into a volumetric flask and adding water to make 1.5 liters of solution. So the question's asking me for molarity, so I'm going to keep that capital M, just like that. And it's asking, so I'm going to need to substitute in moles, and I'm going to need to substitute in liters. Well, actually, I already have the liters, right? 1.50 liters is the volume of my solution. But what I don't know is how many moles 15.5 grams is, right? I can't put 15.5 grams in for here because the unit must be moles. So that's okay. I can convert from grams to moles. One mole of NaCl has a mass of 58.44 grams. That's one sodium and one chlorine. When I divide those two numbers, I get 0.2652 moles of NaCl. I'm not going to round that number. It might keep going. But I'm going to take that number in my calculator and I'm going to divide it by 1.50. And I get 0.177, I get 0.17681, which rounds to three significant figures, 0.177. And I can either put a capital M after it, or I can keep the units of moles per liter. Either way works just fine. Okay, this is another one, but this time I'm giving you the molarity. So how many liters of a 0.114 molar solution of NaOH contains 1.24 moles of NaOH? So the formula is molarity equals moles per liter. I know the molarity is 0.114. The question gives me moles, 1.24. And it is asking me for liters. So now I have to solve for liters. And there's a few different ways that I can do this. I can cross multiply here. And then divide both sides by 0.114 molarity. And when I do that, my liters comes out to be 0.26, 10.877 or 10.9 with three significant figures liters. That's my volume that I would need to have that many moles of that molarity solution. Okay, the last question is a little bit different. It says determine the molar concentration of the sodium ion and the phosphate ion in a 0.15 molar solution of Na3PO4. So we had talked about this a little, maybe in class the last time we met. But when we have an aqueous solution, remember, it will completely dissolve and dissociate. And look at the coefficients here. That for every one sodium phosphate that dissociates, I'm going to make 3 ions of sodium. So if I have 1.50 molarity Na3PO4, when that breaks up, using the coefficients from the balanced chemical equation, for every 1 mole of Na3PO4, I get 3 moles of Na plus. And that would be 4.50 molarity of the Na plus ion. How many moles of the PO4 3 minus ion? Well, if I start out with 1.5 molarity sodium phosphate, Na3PO4, according to the coefficients from the balanced chemical equation, 1 mole of Na3PO4 will just make 1 mole of phosphate. So this would still be 1.50 molarity of that phosphate ion.